Swayam Prabha. Digital India. Educated India.
Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you. And this is the TQM2 lecture series under NPTEL MOOC, and we are going to start the 25th lecture. And as you know that this is 20 hours, that is 40 lectures, and that is spread over 8 weeks. And before I start this 25th lecture, because this being 2nd of January 2018, I would like to wish all of you a very happy new year and a prosperous year, and I am sure everybody would do very well mentally, physically and spiritually for yourself and for the society. With these words, I will start this lecture 25th. Now, if you remember in the last class, which is the 24th one, we had just started an example, and in the example there were 5 factors which were basically mentioned as H time and the rundown time for a circuit, electronic circuit. So, the factors was A, B, C, D, E, and for this example obviously it can change. For this example, for each factors there were 2 levels. Now, also interestingly, for this example you can consider the factors as to be quantitative and qualitative. Like say for example, quantitative can be, so H time can be in minutes or in seconds. Another one can be, say for example, the amount of impurity or the amount of purity of some material, or whatever quality factor which you are using may be very high or very low. Or say for example, humidity may be very high or very low, temperature may be very high and very low, but temperature can also be done on a quantitative scale. So, with this we want to basically see that how the ANOVA modeling can be utilized to basically find out the effects based on the fact that we have basically an hypothesis to test. And remember that the hypothesis would be either for the greater than type or less than type, depending on the level of significance which you want to assign for this. And obviously, for each and every hypothesis, small hypothesis which you have, I will come to that, the level of significance to which it will affect the overall example, overall experiment would differ. So, say for example, in one example it can be to a level of percentage of 1%, in some case it can be 2.5%, it can be 5%, 10%, whatever it is. So, we will see that and basically plan our discussion of the analysis of the problem accordingly. So, if you consider the overall data, so I will just go to the actual example, and as which you always do. So, there are basically 5 factors, so that is A, B, C, D, E, and obviously it will be a fractional factorization model of 2 to the power 5 minus 1, and whatever the level of the Roman concept of level of the problems we will discuss, we will come to that also. But let me go through the examples slowly. So, if you see the slide, in the leftmost column we have the runs. So, basically they start from run 1 to run 16, and in the box or the cell values you have basically as usual, as you can understand, plus and minus significance. Plus means affecting positively and minus means affecting negatively, and the topmost row were basically the factors which we have denoted as I just mentioned few seconds back. It is basically A, B, C, D, E. So, if you note down, let me use the highlighter. So, the factors are A, B, C, D and E, and obviously we will consider that E would basically be a combination of the effects where A, B, C, D's are not there. So, basically we will try to consider them on a standalone basis. Now, when you consider the treatment combination, so say for example, for run 1. So, run 1 basically means the effect of A, if you just look at the cell, they are negative, which means the effects of A, B, C, D are not there, only the effects of E is there. Hence, you see a plus here, which means the treatment combination is coming out to be from factor E. Now, remember, if you are doing the actual ANOVA modeling and you are using the so called regression model, where say for example, y, what are the suffixes, I am going to come to that later, y is equal to mu plus say would be effects of I, which would basically be for factor A, where I basically changes from 1 to A. Then there would be basically the factor only B, this I am talking about standalone basis, only the effect of B, where the suffix would be j changing from 1 to small b, because there is a total number of such effects coming from factors for factor B. Then there would be a factor C, then would be a factor D, then be a factor E. So, it will be I, J, K, L, M. So, that means I, J, K, L, M for A, B, C, D, E, and the last factor would basically be N, where N would change technically here from 1 to N. So, consequently and very interestingly, the suffix and the total number of observations for the number of samples is same. So, N would change from 1 to N, and these I, J, K, L, M would change basically respectively to A, to B, to C, to D, to E. Now, this I am repeating if we have done the modeling as per the norm, where the number of combinations would have been in the next stage would be a combination of 2 taken at a time from this 5, that is 5 C2. So, one of the combinations would be AB, then another would be AC, then AD, AE, then we will go to BC, BD, so on and so forth. Then we will go to the next stage, there would be 3 combinations taken from the 5. So, it will be ABC, ABD and so on and so forth. Then would be 4 combinations at a time taken from the 5, it will be ABCD, ABCE and so on and so forth, and the last one would basically be the combination of 5 taken from the 5, which is ABCDE. Now, for each of these combinations there would be a so called dispersions, and as you remember, they were denoted for the factor A it was tau, factor B it was beta. So, we will basically denote as tau 1 suffix I, tau 1 is basically for A, tau 2 for B, tau 3 for C, tau 4 for D, tau 5 for E, and the suffixes along with this tau 1, tau 2, tau 3, tau 4, tau 5 would basically be I, J, K, L, M respectively, denoting the number of such factors which are there for each. And obviously, then you will basically have in the next step, when you are taking 2 combinations, I will only repeat one, it will be tau 1, tau 2 suffix ij, that means combination of A, B taken together. Then others combinations can be done accordingly. Then when we go to the 3 combinations, it will be tau 1, tau 2, tau 3 suffix ijk when it is A, B, C, and so on and so forth for a combination of 4, and the last one would be tau 1, tau 2, tau 3, tau 4, tau 5 suffix ijk, L, M. Now, in order to do away with that, we considered the fractional factorization, and hence we are discussing this. So, again coming back to the slides, the next row would basically be where the effect of A is there. So, hence the treatment combination would be for only for A, I will highlight that. If I go to the 8th, so repeatedly if I go to the 8th row, the combinations effects are coming positive from A, from B, from C, which is here, 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 and there is no effect from D and E. So, obviously, the treatment combinations are A, B, C. If I go to the 13th row, I am going, I am taking one at a time. You can go from 1, 2, 3, 4, 5, 6 till the 16th one, but I am taking arbitrarily few of them, but the analysis obviously remains the same. So, if I basically take the 13th row, so obvious and it is minus A minus B, but this plus for B for C, D, E. So, hence the treatment combination would be for C, D, E as mentioned here. And when I come to the last row, which is the 16th one, the combinations for all of them are positive, hence the treatment combination would be A, B, C, D, E. Now, if you see the yield that is coming from the data, So, the yields I will just change the color. So, the yields are basically, if you consider, they are for the first one it is 8, second one is 9, so on and so forth, till the second last one which is 44 for the 15th row, which is the combination treatment combination for B, C, D, and for the treatment combination of A, B, C, D, E, the value is 63. Now, when I go to the fractional factorization for the combinations of, because why it is base 2 with 2, I would not use the word base 2, it is 2 to the power 5 minus 1, because for each of these factors there are 2 levels, there are 5 factors, and we are considering this fractional factorization to the level of 2 to the power 5 minus 1 base of a Roman subscript 5, denoting the level of significance which one. The word level of significance I am using is not from the statistical parlance, but basically from the parlance of the discussion which we are having for the last few days, few lectures. Let me use the word lectures. So, if I consider in the combination of E, so E would basically have a positive effect and a negative effect. Now, let us basically now dwell into the effects on positive level inside E, what are the factors, and then for the negative effect for inside E, what are the factors. So, it is like this. So, these are positive and negative for E, and these are the combinations for D which is positive and negative. So, obviously, you will have, now let us consider the combinations as this. At a level of E is 8 or a combination of A, B, E as 52, you have these 3 dimensional figures which we have already discussed, which will give me the combinations for A, B, C, D, E depending on the fact which is positive and which is negative, such that we will be able to find out the fractional factorization diagram. So, which means the design of the experiments for 2 to the power 5 minus 1, depending on each factors as 2 levels, there are 5 factors, and the level of significance is for given by the Roman subscript the 5. So, these combinations can be done accordingly, and remember that when you are basically going to the higher levels, the combinations and would get more complicated, point number 1, and it could also have been done where we could have taken the effects of B, C, D, E, E and then considered A as an effect which basically subsumes all the effects which are not considered under B, C, D, E. That means, E would get replaced by A and the corresponding diagrams could be done accordingly and the table could be done accordingly as just discussed in the previous slide. So, the table 8.7 summarizes the analysis of the variance for the experiment. The model sum of the squares are, one is basically for sum of squares for A, sum of squares for B, sum of squares for C and sum of squares of A, B. So, this comes out to be 5747.25. You can do the calculations accordingly. Remember that I am just mainly harping on the effects rather than going to the calculation, but if you remember the first example which we did for the one was for the aluminum smelting, another was for the battery one. I did go into the details of the calculations, how do you do it. So, but subsequently I am only highlighting the factors which are the factors which are affecting and how the factors are basically being utilized in order to find out the mean square errors and then find out the F statistic. So, remember all this the analysis has been to draw a table where the first column would be the factors, next column would be the sum of squares, then would be the degrees of freedom, then would be the mean square errors, then would be the F value for the F statistic and then the level of significance. So, the overall game plan of trying to tackle any problem remains the same. So, this 5747.25 and this accounts for overall 99% of the total variability in the yield. So, figure 8.7 which is now there here gives the normality plot for the residuals, because that is important to find out whether they are outliers or not, and figure 8.8 is a plot of the residuals versus the predicted values such that we can find out there is a 1-to-1 correspondence with that. So, both those plots are satisfactory, and let me come to this analysis a little bit more in a qualitative sense. So, the sources of variances are as usual that we have basically been able to reduce the fraction using the concept of fractional factorization. So, it is A which is aperture, B is exposure time, C is development time, and the other factor is AB which is aperture and exposure time. So, those values comes out to be, so it is 495.0625 for A, 4590.0625 for B, similarly 473, I am not talking about the decimal part, for C, and for AB which is aperture and development exposure time, it comes out to 189. So, if you add up these values and basically find out the overall percentage with the total error which is 5775, that it comes out to be 99. So, the total error is very insignificant with respect to the total sum of errors. That means, the white noises, you have been able to design the overall experiment in such a way that you have been able to do away with the white noise as far as possible and able to basically find out some plausible reason that what are the effects which are basically affecting your total experiment. So, the degrees of freedom, as I mentioned in just few minutes back, would be the third column. So, the degrees of freedom are given as 1, 1, 1, 1 and 11, 11 is for the errors. The mean square can be found out by, again I am repeating, please forgive me for that. So, for A it will be 495.0625 divided by 1, for the error part it will be, others would be always be divided by 1. So, they would not be changed in the value of the mean square. For the error it would be 28.1875 divided by 11, and the f values again are found out and given by finding out the ratios of the mean square, and this level of significance are given, based on which you can say that what is the p value, based on which you can pass on some judicious judgment about this example. So, if you see the normally plot, so they are almost normal, which should be a 45 degrees line. If you do the or if you go through the basic fundamental concepts of a QQ plot, the plot of the residuals are done in such a way. So, there is almost even balanced amount of dispersion both on the positive side and the negative side of the mean value. So, if which means would mean best technically the average value of the errors is 0 and the standard deviation should basically be sigma square, but it should be remembered that the sigma square value of the errors are independent of time, which I have been repeating time and again from day 1 when we started the concept of design of experiments. The three factors ABC have large positive effects, so which we just saw. So, if the AB factor, which is aperture and exposure time interaction, is plotted in figure 8.9, which is this, and we want to find out with respect to the different other factors what is the overall significance of them. This plot confirms that the yields are higher when both A and B are at the higher level. So, the 2 to the power 5 minus 1 design will collapse into 2 replicates of 2 to the power 3, because now you have basically only 3 A, B, C as there, design in any 3 of the original 5 factors. So, looking at the figure 8.5, it will basically help us to visualize, because now we have been able to do is that try to find out the level of significance. Level of significance means, again I am using this word very broadly, that means the overall effect which is coming out is basically from A, B, C, and others have been subsumed in such a way that we are able to not ignore, I will not use the word ignore, but we have been able to reduce the overall effect for the other factors to the least possible value. So, hence now it becomes, actually it was 2 to the power 5, then we are basically considering 2 to the power 5 minus 1, now it is basically being reduced to the 2 to the power 2 to the power 3, which means that we have been able to grasp our problem to using the simple concept of fractional factorization in such a way that the overall effect is basically being highlighted on only 3 factors and not 5. So, figure 8.10 is basically the cube plot of these factors ABC, which are important, with the average yields superimposed on the 8 corners. So, you have basically, if you see, the effects of A are positive and negative. So, I am taking if A is positive, positive means effect is there, negative is not, no effect. B again I am plotting along this vertical line, along this the plane where I am basically showing you the slide, and C is basically going from this point towards into the slide. So, these are the negative and the positive values. So, if you find out all overall effect, the values at the corner points gives you the overall average values based on which we will do the calculations. Now, we will consider the concept of sequences of fractional factorials or factorizations. So, using fractional factorial design often leads to greater economy and efficiency in the experiment, because we are able to use less number of factors, but basically as a higher level of efficiency, such that overall effect is mimicked by least number of factors, the maximum amount of level of efficiency. Let me use this word. So, they often lead to greater economy and efficiency in experimentation, particularly if the runs can be made sequentially. So, if you can consider that we are taking the factors in such a way, the sequentially we are able to consider the effects in such a way that we are able to eliminate maximum of the factors which are insignificant. For example, suppose that we are investing 4 factors. So, if it is there, it is almost always preferable to run a model of 2 to the power 4 minus 1 suffix Roman subscript 4 fractional design problem, analyze the results and then decide on the best set of runs to perform the experiment in next. That means, if we have basically 4 factors, we take them in this way, analyze and find out the effect of which factors are significant and which are not that significant, hence they can be not eliminated, they need not be considered to that detail, such that the amount of calculation which you want to do would be reduced to the maximum possible extent. If it is necessary to resolve ambiguity, we can always run the alternative fractional models and complete the total set of designs, which is 24. That means that rather than immediately going to do for the combination of 2 to the power 4, we can consider them 2 to the power 4 minus 1 and find out if the efficiency is good. So, we need not consider a greater number of calculations as required. So, the possibilities for the follow up example could have been that we perform one or more confirmation runs to verify conclusions from the initial experiment, or we can add more runs to clarify the results and resolve the aliasing problem, the concept, so that we are able to take the factors which have significance. And the step C could basically be change the scale on one or more of factors, hence which would mean the combinations to or the levels to which we are going to consider for all these factors are on a 1-to-1 parity, and they can be basically considered in the simplest form. So, you add runs. So, if we basically go into the details, the next level of significance would be replicate some runs to improve precision of estimation or to verify that runs were made correctly. The other can be that we add and drop, as we mentioned that if you are considering 5 factors, rather than considering 2 to the power 5, we can consider them 2 to the power 5 minus 1 and basically consider only those factors which are significant, others may not be considered for the combination. Because if you saw that in the last experiment, initially we had 5 factors, but at the end of the day we only took 3 which was A, B, C. The F level of analysis or decisions could be add runs to allow modeling additional terms such as quadratic effects needed because of the curvature of the level of relationship which is there. So, it is not always linear, it can be quadratic also or polynomial. I am using the word polynomial in very general sense, such that we are able to replicate the effect to the maximum degree. And the last way of handling this would be, which is G, is basically to move to a new experimental region that is more likely to contain desirable response values and do our experiment accordingly. We will now consider the 1/4 fraction of 2 to the power k design or 2k design. For a moderately large number of factors, smaller fractions of 2 to the power k design are frequently useful, because if you are able to find out the effect of the factors by consider the effect of the overall factors, how many factors are there, by using the least number of factors, then obviously our calculations are much less cumbersome, and they can be utilized such that we are able to attain the answer in the least possible manner, or least possible calculations or least possible time, whatever it is. So, we consider a 1/4 fraction of 2 to the power k design. This design contains 2 to the power k minus runs and is called the 2 to the power k minus 1 factorial fractions. That means, initially we had 2 to the power k minus 1, now it is 2 to the power k minus 2, and what is that? We will discuss that in details. The 2 to the power k minus 1 design may be constructed by first writing down a basic design consisting of the runs associated with full fractional of k minus k 2 factors, and then associating the 2 additional columns depending. So, the 2, if you remember the table, initially you had the runs, then in the column which I mentioned you had, if you consider the last experiment, it was A, B, C, D, and in E we consider the effects of A, B, C, D. In a way, that means E subsumes all the effects in the very simple parlance which are not being subsumed under A, B, C, D combined together. So, whatever may be the case. Now, what we are going to consider is that consider a second level of division such that we are able to break the factors in such a way that the effects can come out more easily. But remember that trying to be basically be simplistic in our overall calculation would be nice from the computation part, but may not be able to give us the exact answer which you are talking. But if you are able to design and find out the factors as far as possible, then obviously this job is done very carefully and nicely such that we still get the same level of robustness in our answer by or a calculation doing less amount of calculations. Thus let me continue reading the fourth point. Thus, a 1/4 fraction of 2 to the power k design had 2 generators. So, initially if you remember the generator was I. So, if P and Q represent the generators chosen, so obviously we would have P and Q and are called the generating relations for the design. That means, P and Q would be considered the generating design based on which we will do our calculations. The signs of P and Q, either they are plus and minus, determine which one of the 1/4 fraction is produced and which would basically be utilized for our calculation. All 4 fractions associated with the choice of generators for either plus minus P or plus minus Q are and would be the members of the same family, which means that if we are considering plus and minus P or plus and minus Q, the overall set of the factors from where the generators are being formed would be the same. So, the level of significance for A may be positive under P and the level of significance for factor A means and the factor may be negative under the generator Q. So, those answers would be coming out, and the moment we are basically able to differentiate the generators, it will give us the level of significance of the effects which is coming out from the factors A, B, C, D, E, F, whatever it is. That means, I mentioned 6 factors, it can be more or less depending on how you have been able to design. So, this k value 2 to the power k minus 1, k would basically signify now numbers of factors which you are initially taking. So, if it is A, B, C, D, E, F, that means we have basically 6 factors, so k would be 6. The complete defining relation for the design consists of all the columns that are equal to the identity column I. These will basically consist of P and Q. So, we are basically going for a quarter on this factor of k minus 2, hence it is P and Q as generators, and let me continue reading it, and their generalized interaction is basically given as P and Q. That is, the relationship would be I is basically P generations, Q generators, and they would be combinations of P and Q. We call the elements of P, Q and PQ in defining the relations of the words as that P, Q and PQ would basically have the effects which is coming out from all the k number of factors which are there in the example which you are going to consider. The aliases of any effect are produced by the multiplication of the columns for that effect for each word in defining this relationship. So, with this I will end this 25th lecture and continue in 26th about the discussion of the fractional factorization of 2 to the power k minus 1 and consider examples accordingly. Have a nice day. Thank you very much.